Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Part 10: Phi Sensing Technologies Building the Eyes. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once. Time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. We have passed through the gate of literacy. We are now certified readers, interpreters, speakers. We enter a new workshop. Book 10.2, Measurement Engineering. This is where we build the physical eyes and ears of a phi civilization. We move from software and algorithms to hardware, to metal, glass, lasers, and electrons. Today, in part 10.2.1, we begin at the beginning. We learn how to build a machine that can see phi, not infer it from secondary effects, but measure it directly. This is the skill of the instrument maker. You're entering the optical bench lab. Around you are lenses, mirrors on mounts, lasers humming, photodetectors, and oscilloscopes. Your job is to assemble these pieces into an eye that sees not light and dark, but phase itself. Scene: the first glimpse. Picture a perfectly clean, vibration-isolated table. At one end, a laser emits a single, pure, coherent beam of red light. It hits a beam splitter, a half-silvered mirror, and divides into two identical beams. One beam, the reference, travels a straight, protected path. The other, the probe, is sent out to interrogate the world. It might bounce off a microscopic sample, pass through a strange material, or simply travel through empty air. Then, the two beams are brought back together. They meet at another piece of glass, and their combined light falls onto a camera sensor. This is a Mach-Zehnder interferometer. It is the archetypal phi sensor. It doesn't measure the intensity of the probe beam alone. It measures the interference between the probe and the reference. Where the two beams are in phase, they add constructively, creating a bright pixel. Where they are out of phase, they cancel, creating a dark pixel. The pattern of brightness you see, the interferogram, is a direct visual representation of the phase difference between the two paths. Any change in the probe's path length, by even a fraction of the light's wavelength, about 600 nanometers, shifts the pattern. The sensor is exquisitely sensitive to phi. But here lies our core puzzle, the fundamental engineering challenge. How do we translate this beautiful, delicate interference pattern into a precise, numerical measurement of phi? And how do we know the limits of what we can possibly measure? We are not just building a sensor. We are building a sensor that must report its own uncertainty, that must obey the absolute laws of physics, and that must fail gracefully when those limits are reached. The philosophical shift from substance to relationship. First, a crucial shift in perspective. In our holophase view, energy is not a luminous fluid that flows from the laser. It is a tally, a score we keep based on the intensity of change in phi. The laser establishes a highly ordered, coherent phi oscillation, a wave clause. The energy of the beam is our tally of how intense, how rapid that oscillation is. When we use this energy to measure, we are not consuming a substance. We are allowing this ordered phi pattern to interact with the sample. The sample modifies the pattern, it shifts its phase. Our sensor's job is to detect that shift by comparing the modified pattern to the original, unmodified reference. The energy tally is partly scattered into heat, into other directions, and what remains carries the information of the phase shift. This reframes everything. We are not pumping energy into a detector to get a reading. We are carefully comparing two related phi patterns and quantifying their difference. The core mechanism, coherent interference. This leads us to our first and most important coherence criterion for a phi sensor. A valid phi sensor must measure coherent interference. Its signal must arise from the phase-aligned comparison of a probe with a reference or with itself. This criterion rules out vast categories of sensors immediately. A thermometer measures temperature, related to the amplitude of random molecular motion, a form of decoherence. A photodiode measuring only the brightness of a single beam measures intensity, amplitude squared. These cannot access phi directly. They see only the shadows of phi's consequences. To see phi, you must have two coherently related waveforms to compare. You must have a reference. This is why interferometry is not just a technique, it is the fundamental technique for phi sensing. It operationalizes the very concept of phase as a relationship. Heterodyne and homodyne detection are sophisticated versions of this. In heterodyne, you slightly shift the frequency of the reference beam. The interference then produces a beat note, a slow, measurable oscillation whose phase contains the information about the probe's phase shift. This is like tuning two guitar strings to nearly the same note and listening to the pulsating beats to detect tiny differences. But interference is fragile. It requires coherence. The light, or sound, or matter wave in the two paths must be correlated. If the source is incoherent, like a light bulb, the interference pattern washes out into uniform gray. The sensor goes blind to phi. The enemy, noise and the coherence budget. Now we meet the adversary, noise. It is the ever-present whisper of randomness that tries to drown out our signal. In phi measurement, noise has a specific, terrifying power. It destroys coherence. We must understand our coherence budget before we even turn on the laser. This budget defines what is possible. 1. Source coherence budget. Our laser has a coherence length and coherence time. This is the distance or duration over which its waves remain predictable and correlated. If the path difference between our reference and probe beams exceeds the coherence length, interference vanishes. Our budget rule. The maximum measurable path difference must be less than the source's coherence length. 2. Photon budget, shot noise. Light arrives in discrete packets, photons. Even a perfectly stable laser beam delivers photons at random times, following Poisson statistics. This randomness is shot noise. It sets a fundamental limit. If we use very low light to avoid damaging a delicate sample, we get fewer photons, n. The uncertainty in our phase measurement, delta phi, scales as 1 over screte n. This is our quantum mechanical allowance. You cannot beat it without changing the rules, for example using squeezed light, which we'll mention as an advanced concept. Our budget rule. For a desired phase precision, delta phi, we require a minimum photon count, n, approximately 1 over delta phi squared. 3. Thermal and vibration budget. The world is warm and shaky. Atoms in the detector jiggle, creating thermal, Johnson-Nyquist noise. The optical table vibrates, changing path lengths randomly. These are technical noises. They are not fundamental, but they are often the practical limit. Our budget rule. We must cool and isolate our sensor until technical noise is below the shot noise limit, or we must accept that our sensor is not operating at its fundamental best. Our dissonance indicator is clear. A sensor whose output noise does not scale predictably with integration time or probe power is likely dominated by incoherent technical noise. If you double the laser power and the noise doesn't decrease as expected from shot noise, something is shaking or heating. The sensor is fighting itself. If coherence breaks, we stop. If coherence returns, we continue. We cannot make a reliable measurement if vibrational noise is larger than the signal. We must stop, damp the vibrations, improve the isolation. We must work within our coherence budget. The unbreakable law, the Cramer-Rao lower bound. This brings us to the most important safety rail in all of measurement, the Cramer-Rao lower bound, CRLB. The CRLB is not a suggestion. It is a mathematical theorem derived from statistics and quantum mechanics. It states, for any given measurement setup, using a given amount of probe energy, our tally, there is an absolute lower limit to the uncertainty with which you can estimate a parameter like phi. Think of it as the universe's accounting department. You submit an expense report. I used n photons to measure a phase shift. The universe audits it and says, given n photons, the best possible standard deviation for your estimate is this number. You cannot do better. If you claim you did, You are either using a trick we haven't accounted for, like quantum entanglement, or you are miscalculating your error. Therefore, our safety rail is absolute. The CRLB is the floor. Any sensor claiming precision beyond its CRLB for a given energy budget is either using a new physical principle and must demonstrate it, or is miscalibrated, overfitting. This rail protects us from magical thinking. It separates engineering from fantasy. The triunity of a sensor. A good phi sensor is a triunity device. It must handle all three echoes. How fast can it measure? Its detection bandwidth determines how quickly it can respond to changes in phi, high omega. A sensor with low bandwidth will miss rapid phase fluctuations. It averages over time, which can be good for reducing noise, but bad for capturing dynamics. Space echo. How finely can it resolve spatial features? The pixel size of the camera, or the focus of the probe beam, sets its spatial resolution. Its field of view determines how large an area it can see at once. Motion echo. Can it remain stable over the measurement time, or can it track a moving phase feature? This involves active feedback to lock the interferometer or high-speed scanning. Designing a sensor involves balancing these three. A sensor with exquisite spatial resolution might have a tiny field of view. A sensor with extremely high temporal bandwidth might be noisier. The triunity reminds us that a sensor is not just a phase meter. It is a window into phi, with specific properties in time, space, and their interplay. Prediction spine, the hallmarks of a well-understood sensor. From our principles, we can build a prediction spine for any legitimate phi sensor. 1. Shot noise scaling. The measurement uncertainty, delta phi, will scale as 1 over square root of n, where n is the number of coherent probe quanta, photons, phonons, etc. Plot precision versus intensity on a log-log plot, and you should get a line with slope minus 1/2. Deviation from this slope indicates technical noise dominance. 2. Noise spectrum agreement. If you measure the sensor's noise power across different frequencies, its noise power spectral density, it should match the sum of your modeled fundamental noise, shot noise, which is white or flat across frequency, and perhaps thermal noise with a specific profile, and your modeled technical noise, like vibrations at specific frequencies, 60 Hz electrical hum. The model and measurement should agree. 3. Convergence of methods. If you measure the same static phi pattern using two independent, well-designed sensor principles, say a Mach-Zehnder interferometer and the transport of intensity phase retrieval system, which uses multiple intensity images at different focus settings, the two results should converge on the same phi value. Not exactly, but within the respective CRLB predicted uncertainty bounds. This is a powerful cross-validation. Falsifiability. Calling out the impossible. Our falsifiability threads are our weapons against hype and error. Falsifier 1. If a sensor's claimed precision violates its CRLB without a validated, demonstrated novel mechanism, like squeezing, the claim is false, period. It is likely statistical overfitting, where the analysis algorithm mistakenly interprets noise as signal, producing a spuriously precise-looking result. This is the primary falsifier for any new ultra-sensitive phase measurement claim. Falsifier 2. If a sensor cannot reliably reproduce its own measurements of a stable, known phi reference pattern, like a glass slide of calibrated thickness, it is not a usable instrument. It might be unstable, poorly isolated, or misaligned. An instrument that cannot measure a known standard is worse than useless. It is a source of false data. Alternative techniques, the family of eyes. While interferometry is king, it's not the only member of the family. Understanding alternatives deepens our grasp of the core principle. Transport of intensity phase retrieval. This is clever. It doesn't need a separate reference beam. Instead, it takes multiple images of the same sample at slightly different focus settings. The way the intensity pattern transports as you change focus is mathematically tied to the phase gradients. By solving this inverse problem, you can reconstruct phi. Its coherence criterion is different but related. It requires paraxial coherence. The light must be mostly traveling in one direction. It's powerful for samples, like biological cells, that are mostly transparent. Phase contrast microscopy. Invented by Fritz Zernike. It transforms phase shifts into intensity contrasts in a clever optical way, making transparent structures visible. It's a qualitative phi sensor for the human eye, but can be quantified. Holography records both the intensity and the phase of a wavefront by interfering it with a reference wave. The resulting hologram can later be used to reconstruct the full phi field. Each technique has its own coherence budget, its own noise sources, and its own CRLB. A master instrument maker chooses the right eye for the right task. Lanterns across scales, the universal need to see phase. The need to measure phi is not confined to an optics lab. Near scale, medical ultrasound. An ultrasound machine doesn't just measure echo intensity, amplitude. Advanced techniques use phase information from the returning sound waves to create much sharper images, phase aberration correction, and even to measure tiny tissue movements, elastography. The sensor is an array of piezoelectric elements acting as both speakers and microphones, performing coherent interference in time. Middle-scale gravitational wave detectors. LIGO is the ultimate phi sensor. It is a gigantic, exquisitely tuned Michelson interferometer, a cousin of our Mach-Zehnder. Its probe beams travel down 4-kilometer arms. A passing gravitational wave changes the relative length of the arms by a distance 10,000 times smaller than a proton. This minute change manifests as a shift in the interference pattern. LIGO's entire design is an epic battle against noise to stay within a coherence budget that allows it to perceive this whisper of phi from colliding black holes. A single radio telescope dish measures intensity. But when you combine signals from telescopes across the globe, very long baseline interferometry, you are effectively building a single, Earth-sized phi sensor. The timing synchronization between telescopes must be perfect, using atomic clocks, to maintain the coherence needed to measure the phase of incoming radio waves from quasars and black holes. This phase information allows for unbelievably sharp images of the cosmos. In every case, the principles are the same: coherent interference, a battle against noise, a coherence budget, and the fundamental limit, CRLB, set by physics. The ethics of measurement, truth in hardware. Here we encounter a foundational ethic of engineering: instrumental honesty. A sensor that does not report its uncertainty, or whose design ignores its CRLB, is a liar. It presents numbers with a false sense of precision. This leads to false discoveries in science, faulty quality control in manufacturing, and dangerous misdiagnoses in medicine. Building a phi sensor is therefore an ethical act. You are building a tool for perceiving truth. You have a duty to understand its limits and to design it so that those limits are clear to the user. The safety rail of the CRLB is an ethical imperative. It forces humility upon the designer. Furthermore, the Coherence Criterion teaches us that some things cannot be measured directly by a given sensor. Trying to force it leads to nonsense data. The ethical instrument maker knows when to say, "This tool cannot answer that question. You need a different eye." Power without coherence is self-destruction. And the first coherence is between the tool and the truth it claims to reveal. A measurement scene, characterizing the interferometer. Let's walk through our roadmap's measurement scene. Scene, characterizing a Mach-Zehnder interferometer. We place a glass slide of precisely known thickness and refractive index into the probe arm. What we measure. We take many consecutive interferogram images with the camera. We use our unwrapping algorithms from 10.1.1 to compute the phase shift phi introduced by the slide for each image. The pass. We compute the average phase shift from all the images. It matches the theoretical value calculated from the slide's properties and the laser wavelength. Crucially, we look at the variance of our measurements, how much they scatter around the average. This variance matches the Cramer-Rao lower bound predicted for our setup. Based on the laser power, camera quantum efficiency, and integration time, we calculate the theoretical best possible uncertainty. Our actual scatter is close to this bound. The noise is dominated by fundamental shot noise, not technical garbage. The sensor is operating at its theoretical limit. It is a good eye. The measurements are wildly inconsistent from one image to the next. The variance is orders of magnitude larger than the shot noise limit. The average might even be wrong. This indicates dominant technical noise. Perhaps vibrations are shaking the mirrors, or electrical interference is corrupting the camera signal. The sensor is blind to true phi. It's just measuring its own internal chaos. The recognition skill, seeing the need for a fundamental limit. You know you're thinking like an instrument maker when you hear a performance claim and your first thought is, what is the CRLB for that? When you look at the sensor design, you immediately look for the reference path. You ask, what is the source coherence length? What is the expected shot noise? How are vibrations suppressed? You think in budgets and bounds, not just in features and specs. The digital twin, the virtual optical bench. Our twin now becomes a sensor simulator. We can model the entire interferometer, laser coherence, beam splitters, mirrors, sample, camera noise. We can simulate the passage of individual photons, Monte Carlo simulation. We can add synthetic vibrations and thermal drift. Before we cut metal or align a single mirror, we design and test the sensor in the twin. We predict its CRLB. We see how susceptible it is to various noise sources. We iterate the design virtually until its simulated performance meets our needs. This transforms instrument making from a black art into a predictive engineering discipline. Enabling the future, the foundation of all engineering. This skill, phi sensing technologies, depends on the concept of phi and its reconstruction. You must know what you're trying to measure before you can build a tool to measure it. It enables everything that follows in measurement and beyond. All derivative measurement, 10.2.2. To measure omega and k, you first need a clean phi signal from a capable sensor. Foundry design, 10.4.0. To build machines that write phi patterns, foundries, you need sensors to monitor what they're writing to provide feedback to ensure they are creating coherent structures and not chaos. The roadmap states it perfectly. You cannot engineer what you cannot measure. This part is about building the first, most fundamental measuring tool. All control depends on sensing. All feedback loops begin here, at the optical bench. Zenodo and the mathematical limits. If you want to see the full mathematical derivations and exact equations behind this idea, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. The papers will present the derivation of the CRLB for phase estimation in an interferometer. It will involve Fisher information, quantum states of light, and the statistics of photon counting. They will formalize the noise models, the spectral density of shot noise, 2H Nudra P, where P is power, the Johnson-Nyquist formula for thermal noise, 4kTb. They turn our qualitative budgets into quantitative computable limits. Return to the phi. Let's zoom out. We have taken our first step into the hardware world. We have learned that to see the fundamental field phi, we must build machines that perform coherent interference. These machines are not magic. They obey strict budgets set by coherence, quantum mechanics, and thermodynamics. Their ultimate performance is capped by the Cramer-Rao lower bound, a law as unbreakable as the second law of thermodynamics. We remember, there is only one field. Our sensors are delicate arrangements of matter, designed to let two copies of a phi ripple from that field meet and tell us about their difference. The sensor itself is a pattern in phi, designed to resonate with and reveal other patterns. We have added a new concrete discipline, the analysis of every sensor through the lenses of Coherence Criterion, noise budgeting, and the CRLB safety rail. We build eyes that know the limits of their own sight. So, picture yourself back at the optical bench. The laser is on, casting a sharp red dot. You've aligned the mirrors. You place a hair in the probe beam. On the camera screen, instead of a shadow, you see a beautiful, intricate pattern of ripples and dark bands swirling around the silhouette. That pattern is the phase distortion caused by the hair. You have built a machine that sees not the hair, but the effect of the hair on the phase of light. You are seeing the world in phi. You have just learned to build the first eye of a phi civilization. This is part 10.2.1, Phi Sensing Technologies, Building the Eyes. It is the foundation of book 10.2, Measurement Engineering, and the practical implementation of our literacy. In our next session, we will use this eye not just to see static phi, but to see it changing. We will learn to measure its verbs, the temporal rhythm omega and the spatial pattern k. We will build the tools to see not just the landscape, but the wind moving across it and the shape of its hills and valleys. Remember, one field phi with its infinite echoes in time, space, and motion. We have now built the first instrument to hear those echoes clearly. Our conversation with reality has just gained its first, precise vocabulary of observation. Salam, and peace be upon you.